Scientists are proposing a new potential energy source that could support extraterrestrial life on Europa, one of Jupiter's moons. Radioactive elements slowly seeping from rocks into the moon's ocean, where they could generate enough energy to sustain living organisms. Research presented at the American Geophysical Union's annual meeting in New Orleans introduces a new model for Europa's habitability. Rather than relying on the moon's internal heat, the model suggests that chemical energy released from radioactive rocks may be the key factor making Europa potentially life-friendly. NASA's Europa Clipper mission, launched in 2024, is expected to test this hypothesis when it arrives in the Jovian system around 2030. The idea was developed by Ngoc Tuan Trong, a planetary scientist at NASA's Goddard Space Flight Center, who drew inspiration from extreme environments on Earth, according to Science magazine. On our planet, microscopic organisms living deep in the ocean survive without sunlight, instead relying on chemical reactions to produce energy, a process known as chemosynthesis. Scientists believe a similar mechanism could be operating on Europa. Beneath Europa's icy surface lies a vast saltwater ocean containing more than twice the volume of all Earth's oceans combined. This enormous reserve of liquid water, a fundamental requirement for life, has made Europa a prime target in the search for life beyond Earth. Unlike neighboring ocean moons such as Ganymede and Callisto, Europa's ocean is thought to be in direct contact with hot, rocky material on the seafloor, according to NASA. Over time, radioactive materials within these rocks could leak into the ocean. As these elements naturally decay, they would release heat and split water molecules into hydrogen and oxygen ions. Microbial life could potentially harness the energy stored in these ions to survive, the study suggests. To explore this possibility, Trong and his team modeled the concentrations of 3 radioactive isotopes believed to be present in Europa's ocean: uranium-235, uranium-238, and potassium. They calculated how many ions would be produced through radioactive decay and found that the energy generated could support a substantial amount of life, enough to power approximately 1 septillion cells, equivalent to the biomass of about 1,000 blue whales. Previously, scientists assumed that heat from Europa's rocky interior was sufficient to sustain life. However, recent research indicates that the moon's icy shell is much thicker than once thought, making it unlikely that internal heat alone could provide enough energy. Radioactive elements, therefore, offer an alternative explanation for how Europa might generate the energy needed to support early life forms.